Light and its effects. Learn about how light is formed, how it helps us every day, and much more by diving into the pages of this engaging ebook. Table of contents, light in the universe, waves of light, traveling light, what do you see, particles of light, power of light, think like a scientist, glossary, index, your turn. Light in the universe. We wake up when light streams through our windows in the morning. We know our day will wind down after sunset. We turn on the lights first thing in the morning, turning them off only when our day is done. So, of course, we know what light is. At least, we assume we know what light is. But ask yourself, what makes up light? Most things in the universe are made up of matter. Matter is made up of tiny particles called atoms. Light can behave just like one of these particles, but light isn't matter, and it doesn't always work like a particle either. Instead, it acts like a wave. Light is a special form of energy. It can move faster than anything else in the universe. It can travel in a straight path, or it can bend and turn. And it can even pass through objects. Even though we think we understand light because it's all around us, there's a lot more to it than meets the eye. The history of sight. In the past, many people believed that sight came from light that was shining out of our eyes. It was called emission theory. It wasn't until the 11th century that this theory changed, when a scientist named Ibn al-Haytham published his findings. People finally started to understand the truth about sight. He said that light reflects off objects and goes into the eyes to create sight. Waves of light. We often think of water when we see the word waves, but light can travel in waves too. In the same way a ribbon ripples when it's tugged from one end, waves have an up and down pattern. Even though we see light, we can't see these waves. Light. We don't think of light as having much of an appearance. That's because white light, like the light the sun gives off, seems colorless. In truth, white light contains a spectrum or range of colors. If you were to break it up to see all of its parts, you would find a rainbow of color. It contains red, orange, yellow, green, blue, indigo, and violet. When we observe light, we're really observing electromagnetic radiation. Light has wavelengths that we can see. A wavelength is a measure of distance between two peaks of the same wave. All of the colors that make up the visible spectrum. Red has the longest wavelength. Violet has the shortest. But visible light is just a small part of a range that we call the electromagnetic spectrum. We can't see the other wavelengths in this range, but we can observe them. So sunlight takes time to travel to Earth. The light we see is actually from 8 minutes and 20 seconds ago. An indoor rainbow. To split light into a visible spectrum, fill a container with water, then move it into a sunlit window. Place a small mirror in the water and angle it towards the sun. A rainbow will appear on the wall. The rest of the spectrum. Ultraviolet UV waves have shorter wavelengths and more energy than visible light. Our skin absorbs UV rays, sometimes causing a sunburn. We can't see these rays, but they can damage our skin and our eyes. X-rays have shorter wavelengths and even more energy. They don't just seep into skin, they pass through it. So we use them to look at our bones. They are also used to inspect luggage at airports. The wave in the shortest wavelength is the gamma wave. It has the most energy of any wave. It's so powerful, it can kill cells. We often use it to eliminate cancer cells from the body. On the other end of the spectrum is infrared. Infrared has a longer wavelength and less energy than visible light. We can detect its energy when we feel heat from fire. We use this wavelength in remote controls. We also use it in night vision goggles. We even use it to toast bread. The wavelengths of microwaves are even longer. Those waves help us to send information through space with satellites. They even help us cook. In fact, the microwave appliance uses this wave and was named after it. Radio waves have the longest wavelength and the least energy. We communicate with them because their length allows them to reach other places that other waves can't. They even bend around obstacles such as houses. So you have gamma waves, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. Spiders can see UV light. Shades that shield. Ultraviolet rays can be helpful. They help your body create vitamin D, but they can also be harmful to your skin and eyes. For UV protection, use sunglasses and sunscreen. The higher the sun protection factor, the SPF, the more protection you're going to be getting from harmful rays. Traveling light. Light waves don't just float around us randomly. They all come from a source. The sun is a light source. A flashlight is another. You don't usually use your television or computer to light up a room, but they're light sources too. Reflection. Not every object is a light source, but all objects reflect light. That reflected light enables us to use objects while giving it color. When white light bounces off a red marble, not all the light is reflected, only the red waves. The marble absorbs the remaining colors of the visible spectrum. Every surface absorbs and reflects different wavelengths, giving each object its unique color. White surfaces reflect all colors. That's why they appear so bright. Objects with black surfaces absorb almost all colors. Feel the heat. When the sun's energy is absorbed, it creates heat. That's why your skin gets warm in the sun. Seeing things. Why can we see things when it's light out, but not when it's dark? Light hits objects and bounces off of them. When the light reaches our eyes, we can see the object. Without light, we can't see. All light travels in a straight line. Radio waves are able to curve around objects due to their extremely long wavelength. Visible light has no such advantage. When it strikes something that is opaque or solid, the object blocks the light's path. It absorbs or reflects the light. A shadow forms where the light would have continued on its path. That's why shadows always appear on the opposite side of a light source. But not all objects are opaque. Glass, for example, allows light to pass through. That's why we have windows in our home. See-through objects such as glass are often transparent. They don't cast shadows. They simply allow light to continue along its path. In other words, they transmit light. When an object is only partly transparent, we call it translucent. One example is a colored balloon. The balloon blocks some of the light, thus it casts a shadow. It also lets some of the light through, so the shadow contains color reflected from the balloon. So stained glass windows have colored glass that is translucent. So translucent, remember, allows light to pass through, giving that color as it goes through. Transparent, remember, is when light is able to completely pass through and we can see through it. Okay? Opaque remember, means that it is blocking and we cannot see through it. So see how like our shadow is like blocked out. So making stained glass is an ancient art that can be traced back to the early Egyptians. Refraction. Visible light casts shadows because it can't curve around solid objects. It must follow a straight path. There are two instances when visible light can bend or change direction. Reflection is the first instance. The second is called refraction. Refraction occurs when light moves from one material to another, such as from air to water. In this case, water slows the light. That makes the objects in the water appear different than normal. For example, a fish may look larger than it really is, or an object only partly in the water may look broken where the water meets the air. These odd visual effects are the result of light waves bending. Rainbows are also produced by refraction. The sun hits the water in the air, and the light waves slow and bend when they hit the water. Each color making up white light has a slightly different wavelength, so each bends at a slightly different angle. White light separates. As a result, we see a rainbow overhead. So here we see kind of how this looks in a telescope. You have the lens, you have the light coming through, it flips, and we can kind of see it in the eyepiece. It's all clear. Like water, glass and plastic also refract light. Refractor telescopes work by focusing these light waves in a particular spot. Light enters one end of the telescope. The objective lens bends the light to a focus or point. The eyepiece magnifies or enlarges the image. So here we have visible light. So visible light's coming in. It's going through the prism and it is breaking apart the light, and it is showing all the colors of the visible spectrum. What do you see? Not all surfaces reflect or absorb light in the same way. We already know that light-colored objects reflect more light. They draw our eye and our attention because of this. A mirage. Many thirsty travelers have been fooled by the effects of refraction on a hot day. A mirage occurs because warm air refracts light rays near the ground. The result is an illusion of water in the distance. So see that illusion of water? Color and shine. We are much more likely to notice a bright orange cone in the road than a dark gray one. And yellow flowers stand out more than purple ones. But some objects shine despite their color. A brand new black car doesn't look dull. That's because it has a smooth surface. How smooth or rough an object is affects its ability to reflect light. Light bounces off all surfaces, but smooth, even surfaces reflect light in a straight path. That produces a stronger reflection. The reflected light also produces a shiny look. So how a laser works. Lasers are made using mirrors. Inside the device, light waves move back and forth between two mirrors. This causes the light to build energy. Energy is released as a thin beam. Unlike most light, all light from a laser has the same wavelength. As a result, the light doesn't scatter. Caution, lasers produce light waves that may damage your eyes. Distortion and scattering. Mirrors reflect light better than any surface. They reflect light so well that we can see any object that's directly in front of a mirror reflected right back. The polished surface of a new car reflects so much light that it's almost like a mirror. But if you look at yourself in the surface of a car, your image isn't going to look like the one that you see in the bathroom mirror. Objects with curves don't reflect light in a perfectly straight path. As smooth and even as a car's surface is, it's not as flat as your mirror at home. The curves of the car break apart the direct path of light. As a result, the reflected light is scattered. Your reflection looks distorted. Mirror, mirror on the wall. There are 3 types of mirrors. Plain mirrors are simple flat mirrors, like the ones in your bathroom. Concave mirrors curve inward, and convex mirrors curve outward. Distortion happens with light-colored objects too. Toasters have a shiny light-colored surface, just like the mirrors, but the reflections you see in them doesn't look exactly like you. The curves reflect an odd version of you. Scattering creates this effect. Funhouse mirrors work in the same manner. The mirrors are deliberately curved and warped to produce strange-looking reflections. These mirrors aren't like the flat ones we hang home to check our appearance. So we have light reflected off smooth surfaces, and light off a rough surface kind of bounces all over. Scattering even occurs when objects we would expect to be transparent. When we use glass for windows, light transmits through them. But when glass hits the texture, it obstructs or blocks the light from taking a straight path. Even a small curve in the glass will cause light to scatter. As a result, the glass is no longer transparent. These surfaces are translucent. Textured glass is often used for shower doors and bathroom windows because it provides both light and privacy. Textured glass is a bit bumpy, but some surfaces are so rough that they scatter light in all directions. Consider, for example, the rough bark of a tree. Every slight bump or crack makes the light bounce in another direction. The light we see is so scattered, we can't see the shine of a reflection. That's why a tree's surface looks dull instead of shiny. In the same manner, a rough, uncut diamond has very little shine, but master jewelers polish and cut these stones to achieve a brilliant shine. They base their designs on their scientific knowledge of reflected light. So onions become translucent when cooked because the chemicals and water that the onions have make them opaque and evaporate during cooking. Here we have a glass frog. Translucent and transparent animals. There are animals that are translucent and transparent. Glass frogs are green like other frogs, but they are translucent. You can see their organs through their skin. A glass wing butterfly has transparent wings with brown borders. Particles of light. Waves explain most of light's traits, but light can also act as a particle. To see this, we turn to the atom. The atom is a small bit of matter in the world around us. Every object, from our toes to our toys, is made of atoms. Atoms contain even smaller particles. Neutrons and protons huddle at the center of the atom. Around the neutrons and protons are small spaces called orbitals. Electrons are located in these spaces. They move inside the orbitals, but not in a set path. This means that you never know where an electron will go next. When an atom is energized, its electrons move to higher orbitals. In time, electrons drop back to their normal orbital. To do so, they let go of any extra energy. That energy is given off as photons. Photons are the base unit of light. So a photon is a tiny particle of light. Albert Einstein originally discovered photons, but he called them energy quanta. Gilbert N. Lewis was the first scientist to call them photons. Electromagnetic radiation. The behavior of electrons giving and receiving photons is why light is called electromagnetic radiation. So light isn't matter. It is energy given off by the behavior of electrons. Even so, photons have like particles when they interact with matter. Matter can absorb the energy of a photon. When it does, we feel this transfer of energy as heat. Photons are what make up the sand on the beach warm. The sand absorbs the photons from the sunlight, warming our toes. Photons also interact with our eyes. When a photon of light meets the eye, it becomes electrical energy. The energy is transformed to our brains to form an image. Photons help us see. Photons can travel at the speed of light. That's a whopping 299,338 kilometers per second, or 186,000 miles. The fastest jet in the world would take 4.5 hours to go all the way around the planet once. But at the speed of light, you could make that same trip 7.5 times. And it would only take you 1 second. Light fight. Lightsabers are less science fiction than we once assumed. We always thought photons couldn't interact, but recent research has shown that photons can bind together to form molecules, and when they interact, they can push against each other and deflect. Duality. Light can act as a wave like a particle. This is stated in wave-particle duality theory. Albert Einstein worked with other scientists, paving the way for this theory. Power of light. We take light for granted because it's always present. But imagine what our world would be like without it. Light gives us sight. It allows us to see color. It provides us with warmth that keeps us healthy. It even helps us communicate. We know plenty about light. We're aware of the way it's absorbed and reflected to create color. We understand how refraction and scattering cause distorted images. And we know that a lot more to light than just what the eye can see. We also know a little about photons and how they affect our vision and the temperature of objects. But light is no ordinary energy. There's so much more left to learn about how it works and what it can do. Scientists still hope to uncover the secret to how they can act as both a wave and a particle, and they were always seeking new ways to use its power. For the rest of my life, I will reflect on what light is. Albert Einstein. All right, so we're going to go ahead and stop there.